Hello good people, I'm going to talk about atomic radii and a couple of associated periodic trends. Note that the word radii is the plural form for radius. I'm going to focus on the main group elements. So let me bring in a graphical representation of their radii. All of these beautiful red spheres represent the radii of the main group elements. To make it easier, let me bring in the symbols as well as the value for their radii in picometers. A picometer is a trillionth of a meter. And so, in case you forgot, this is a reminder that atoms are very, very tiny. By inspection alone, you might note a few things. For example, as we go down a group, the red spheres representing the size of the atoms become bigger. And so we could say that as we go down a group, the radius of an atom increases. This trend can be explained in terms of energy levels. As we go down a group, the outer energy level N increases. This means that the valence electrons of an atom are further away from the nucleus. Recall that the period number indicates the energy level of the outermost orbital. For example, lithium is in period 2. Its outermost orbital is on the second energy level. Potassium is in period 4. Its outermost orbital is on the fourth energy level. And as the fourth energy level is further away than the second, it means that the valence electrons of potassium are further away than the valence electrons of lithium. And so the overall atomic radius is greater for potassium than it is for lithium. With respect to the atomic radii, there is another easily observable trend. As we move across a period, the atomic radii decrease. This decrease in the size of the atomic radii can be explained, in part at least, due to the shielding effect of the core electrons. I'm going to use lithium and neon to hopefully demonstrate. These two red spheres that I'm drawing in right now represent the nuclei of lithium and neon down here. Within the nucleus of lithium, I have 3 protons. Within the nucleus of neon, I have 10 protons. Both lithium and neon are within the second period, which means both of them have 2 energy levels. Or more precisely, both of them have the outermost orbitals that are in the second energy level. Let me draw in the energy levels. I'm using the Bohr model of the atom, where I'm using concentric circles to represent different energy levels. The circle closest to the nucleus is energy level 1, and the next one out is energy level 2. Energy level 1 can carry a maximum of 2 electrons. So let me draw those in. 2 electrons for lithium, 2 electrons for neon. Energy level 2 can accommodate a maximum of 8 electrons. In case of lithium though, we only have 1 in the second energy level. Recall that in a neutral or ground state atom, the number of protons has to equal the number of electrons. The second energy level of neon carries 8 electrons, the maximum. Alright, so what are core electrons? Recall that the valence electrons are all the electrons in the outermost energy level. All of the other electrons are referred to as core electrons. So in case of lithium, we have 2 core electrons and 1 valence electron. In case of neon, we have 2 core electrons and 8 valence electrons. Shielding effect, in its simple form, can be explained as follows. The core electrons shield the valence electrons from the pull of the protons inside the nucleus. Recall that there is an electrostatic attraction between the electrons and the protons. If I now compare lithium and neon, I can see that they have the same number of shielding electrons, 2. But what are they shielding? That is different. In case of lithium, the 2 electrons shield 3 protons. In case of neon, the 2 electrons shield 10 protons. We could say that the shielding effect of the core electrons of neon is not as effective, because they are trying to shield more protons. This in turn means that the valence electron of neon experience a greater pull towards the nucleus. They are being pulled by more protons. This means that the valence electrons of neon will be a little bit closer to the nucleus, whereas the valence electron of lithium will be a little bit further out. It is being pulled in by fewer protons. As you may suspect, there is more to this story, but for now we'll leave it at that. There is one more point I would like to make. The size of the atomic radii can be used to explain certain behaviors of atoms. The smaller the atomic radius, the tighter the hold on the electrons, and so the harder it is to remove an electron from an atom. For example, let me look at sodium here on the left and chlorine here on the right. Sodium has a much bigger radius. This means that it is easier to remove a valence electron from it. The valence electron of sodium is further out than the valence electrons of chlorine. This means that the valence electron of sodium experiences a lesser pull by the protons in the nucleus. This in turn means we need less energy to remove it from sodium. This fits neatly with respect to atoms that donate electrons and atoms that gain electrons. Recall that metals, such as sodium, will donate electrons and become cations, whereas nonmetals, such as chlorine, will accept electrons and become anions. Yes, it is true. Whether something accepts or donates electrons also depends on achieving a stable electron configuration. But now we can also explain that behavior in terms of atomic radii. Atoms with bigger atomic radii, such as metals, are far more likely to donate electrons than atoms with smaller atomic radii, such as nonmetals like chlorine. In summary, atomic radii increase as we go down the group, but they decrease as we go across a period. The smaller the atomic radius, the greater the electrostatic attraction between the protons and the valence electrons. In turn, this means it is harder to remove an electron. Or conversely, we could simply say, the bigger the atomic radius, the easier it is to remove a valence electron. I can already hear many voices cursing my name and questioning my heritage. And so, that is all for now, and I will see you on the flip side.